Uh, Okay, the exam on the 22nd, closed book, closed note, no calculators. What else? The final review. A review for final. That's 10, put 10, 12, 17th, right? It's this Friday. I have questions ready. Okay, the way I do a review is I come in and I'll answer any questions that people have, and I'll keep answering them as long as people have them. And then once the questions stop, the review stops. And was there something else I wanted to put up here? Oh yeah, about the homeworks. So homework 4 and 5 are being returned. You can pick up 6 and 7. When they're ready, which I'm not in complete control over, but it should be ready. 6 should be ready very soon, and 7 should be ready in lounge next to my office. And this is homework 4 and 5. Sorry, why don't we just take them both? And old homeworks are in there too. Okay. Everybody showed up today. All right, which is ironic because we've already covered everything that'll be on the final. I wanted to cover one last. Item, which I think you should know, but because I won't have to work on it, it won't be on the final. And then we'll do a quick review, just generally what the topics are going to be that you're supposed to know. So, if you're interested, take notes and pay attention. If you're not, if you just want to get going for the grade, take a 20-minute break. What we're going to talk about is fairness. In particular, we're going to talk about max-min fairness. So we looked at two flows going through a link or a pipe. There's a pipe at capacity C. Or let's say you've got n flows going through this pipe. Okay, I mean, in my picture, n is 4. So what's a fair allocation? Right. What's the allocation you could give all these flows where no flow would complain? It would be C over 4, right? Or C over n. Right, 1 n of the total capacity. Right. But what happens when you have a situation like so? So let's say this link has capacity 1, and let's say this link has, let's make it capacity 10. Let's make it capacity 8. Why not? Yeah, let's make it capacity 8. And have some other link here and another link here. Okay, and we know flows don't always go to the same place, right? So what happens again if I have 4 flows? They all through this pipe, and then 2 of them go this way, and 2 of them go this way. Okay, let me label them F1, F2, F3, and F4. So flow Fi is given rate Ri. Okay, what is a fair set of rates Ri? And the rule is that the sum of flow rates cannot exceed the capacity of the link they flow through. Okay? So I've got four flows, right? They all go through a link of capacity 8. So I could assign them all a rate of 2, right? Now that would fully utilize this link. But then, well, the 2 that go over here, that's okay. They each are given a rate of 2. Their rates sum to 4, so they go through this link. But the 2 that come down through here, right? If I give them each a rate of 2, they're going to overutilize this link here, right? So you can't do that. So the question is, how do you break up the rates such that they're fair? Okay, and maximum fairness is probably the best notion of fair. So for instance, let's just assign the max and fair rates. What I would do is I would give each of these 2, and each of these 1. Excuse me. Okay. So let me just do one more example. Just change it a little bit. Let's make this 8. Let's make this 6. I'm just going to keep this at 2. I'll have the 4 flows going through. Okay, the maximum fair rate in this case would be 3, 3, 1, and 1. Okay, and the only reason I just want to put this example is that, what was my point? Sorry, let me make one other change. Let's make this 10. Now the fair rate would stay 3, 3, 1, right? I mean, before these links were both constraining me in the example above, right? It was the links at the end that were constraining things, meaning I wasn't fully utilizing the capacity of that first link. Now I'm fully utilizing the capacity of this link, and I'm fully utilizing the capacity of this link, and this link isn't fully utilized. Okay? People get the idea? Okay, so what's the rule of the maximum fair allocation? Let me say this. Let's do an allocation is an assignment of rates R1, R2, dot, 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 Rn to all flows F1, F2, after that, Fn in a network. Okay? All right. So an allocation is assignment of rates R1 through Rn of flows to a set of flows in a network. Okay, I'm going to write let S sub L be the set of flows that traverse link L. Okay, so for example, the link up there 8, S sub L is going to be F1, F2, F3, F4. For the link with capacity 4, S sub L is going to be F1 and F2. Okay? An allocation is feasible if for all links L in the network, some okay. So an allocation is just a set of rates assigned to flows. An allocation is feasible if on every link, the sum of the flows that go across that link don't exceed the capacity of the link. Okay, that's what that formula is there, right? C sub L is the capacity of the link L. I'm summing up over the flows that traverse that link L. I'm summing up their rates. As long as the rates don't exceed the capacity of the link, the allocation is feasible. Okay. The max and fair allocation. So let me call this A. A is this set of rates. It's max min fair if it is feasible and, let's make sure I get this right now. Yeah. Okay, if I increase any flow's rate from AI to RI, okay. Sorry, no, let me not do it this way. Let me do it this way. If any flow's rate is increased from AR to IRI, Okay. So that's the definition of maximum fair. So an allocation is maximum fair if you try to increase any flow's rate, okay, take any flow I and try to increase its rate, then, sorry, that's not if any flow Fi, it's if flow Fi. Every flow Fi, comma, if its rate is increased. Okay. So an allocation is maximum fair. If you take the set of rates, if you try to increase somebody's rate, take a flow and try to give it more of the bandwidth, in order to keep the allocation feasible, you're going to have to take another flow that had the same or less bandwidth to begin with and reduce it. Okay. So it's sort of like you're taking from the poor or the equally funded and giving to the equally funded or rich, right? Which is never fair. Right. So okay. In these examples, why are these all maximum fair? Let's take a look. We had this pipe of 8, a pipe of 4, or a link with capacity 4, and a link with capacity 2. And I claim this allocation 2211 was maximum fair. Okay, so why is it maximum fair? To show it's maximum fair, what you have to do is take every flow and try and increase its rate by a little bit. And you'll see that when we try to increase that flow's rate, in order to keep the allocation feasible, you're going to take another flow who had the same or less rate to begin with and decrease that. Okay? So for instance, suppose you took this flow here and you increased it. Right, let's make it 2 plus epsilon. Right? Well, now this pipe here is overloaded, right? We're sending 4 plus epsilon through it. So the only way to make the allocation feasible again and not overflow this pipe is to reduce the other flow, one of the other flows that's going through it. In this case, this other flow of weight 2. Right? Its rate would have to drop from 2 to 2 minus epsilon. So I took 2 flows that were equal. By giving any amount you gave to one of them, you'd have to take away some of that from the other. So in some sense, that's not fair. Right? Why should this flow be able to get a higher rate at the expense of this other flow? So you're not allowed to do that in this case. Okay? And it's a symmetrical case. So if I added epsilon to the second one, I'd have to take away epsilon from the first one. And similarly, if I added epsilon to this flow, they both go through this pipe and they're constrained over here, I would have to take away epsilon from this other flow over here. Okay? If you look at the other case, drew up. What do we have? 10 and 2. Right, and I said the maximum fair allocation was 3311. Okay, why is this not maximum fair? Well, if I increase one of these guys by epsilon, right? Suppose I increase this flow by epsilon, then I can somehow I've split up the decrease among these 3, right? They're constrained by this pipe. No matter who I take it from, I'm unfairly penalized. Okay. If I gave a little bit more to one of these 2, right? Let's say I give epsilon more to one of these guys. Well, in order to not overflow this pipe, I could take away epsilon from the 3. That's okay. I'm taking away from a rich and giving to a poorer. But it's this pipe that's going to be the problem, right? When I add epsilon to this guy over here, the only other flow that goes through that pipe is the other one. I'll have to take away from him, right? So again, I'm forced every time. If the allocation is maximum fair, if I try to give more flow to more of a rate to any flow, then I'm forced to take away from somebody who has less or equal to begin with. Okay, and there's a result that says every network has one and only one maximum fair allocation. Okay, so that means for every other allocation, that is not maximum fair, a flow can be found whose rate can be reduced, whose rate can be increased, sorry, without penalizing a flow with equal or lesser bandwidth. Okay, so for instance, let's do okay, so let's pick values for F1, F2, F3, F4, such that we have a feasible allocation. Let's look at whether or not it's maximum fair. So people just take some guesses. Just give me some rates for. Let's do a rate of 1 for every flow. Okay, and we'll see why that's not max fair. So what if we assign them all rates of 1? Right? Then flow 1. Obviously, it's the only flow going through this link. So if you increase the rate of flow 1, you're going to exceed the capacity of this link. So that cannot be done. What about flow 2? Flow 2 goes to this link, and I guess it's kind of, can people sort of tell this is flow 2 going across over here? Flow 2 goes through this link here, where if we assign every flow a rate of 3, 3 units of capacity are being used, and over here, 2 units of capacity are being used, right? So I could increase flow 2's rate from 1 to 2, and that's still a feasible allocation, right? I haven't exceeded the rate of any link, so I was able to increase a flow's rate without decreasing another flow's rate, right? Suppose I did 1, 8, 1, 0. Okay, this is feasible, right? The first, I could even do 1, 1, 8, 1, 2, or 3. Right, this is feasible. I'm utilizing this link to full capacity. I'm not exceeding it. I'm utilizing this link to full capacity. I'm not exceeding it. This one I am exceeding capacity, right? Yeah. So sorry. So let's make this 7 instead. Right, the other allocation wasn't feasible. Now, this is being used full capacity. This is being used to full capacity. This is being used to full capacity, and this is not being used full capacity, but that's okay. Okay? Why is this allocation not max min fair? Well, for instance, I could increase F3 from rate 1 to rate 2, right? Now I'm exceeding this link's capacity, but I can reduce F2 from 7 to 6, right? In this case, I gave some additional rate to one flow, and I took away the rate from a flow that had more to begin with. That's okay. And so the original allocation was not maximum fair because I was able to find a richer flow that I could steal bandwidth from and give it to the poorer flow. And when you can't do that, the allocation is maximum fair. Gary?
Wouldn't you have to reduce the flow F4?
What do you mean F2? Why did I reduce it from?
No, I mean, because you increased F3, then you have to decrease F4.
Yes, that's right. I would have had, yeah, to keep it feasible through this link, I would have had to have decreased F4 as well, right? But again, I increased a poor flow from 1 to 2, and I decreased a richer flow from 3 to 2, right? I decreased 2 flows. They were both richer. They had more to begin with than the flow which I increased. Okay. So what is the maximum fair allocation for this? It's going to be F1 is going to get 1. F4 is going to get 3. F3 is going to get, wait. F4 is going to get 2. F3 is going to get 2. 2. And F2 is going to get 6. Okay, I think this is the maximum fair allocation. So try and increase any flow here, okay? And you'll see stealing from a flow of lesser value won't do you any good. So for instance, if I try to increase F3 or F4, it's this link that's going to give me the problem, right? If I try to increase F3, I'm going to have to decrease F4. And if I try to increase F4, I'm going to have to decrease F3. I can't increase F1, right? If I increase it, I'll get an infeasible allocation. There's no way to increase F1 without breaking the feasibility. And obviously, if I increase F2, right, I'm going to have to steal from some other flow. And F2 is the flow of largest bandwidth. So I'll always have to steal from a flow that had less to begin with. So this is the maximum fair allocation. Okay? And there's a very simple algorithm to compute the maximum fair allocation. So I'll just present that, and then that'll be it for this topic. Okay, it's a filling algorithm. You start with everything equal to 0. Okay, and then you continuously increase the flow rates, growing at the same rate. So increase the R sub I speed. I'm going to say speed because I don't want to overuse rate. And only stop increasing those flows when it crosses a link whose capacity is fully utilized. Okay, so let's look at this one example real quick. Where I said the maximum fair allocation was 1622. Let's use this filling idea. So you start with all the rates equal to 0, okay, and you gradually increase them continuously. So they go, an eighth, a quarter, a half. You keep growing them, and none of the links have reached full capacity yet. Okay? And then when we get to 1, all right, at that point, the link on top there with capacity 1 has reached full capacity. So we have to stop growing flow 1's rate. So flow 1 gets fixed at 1, and we continue to grow all the other flows rates. Okay, so flow 1 is 1, and the others grow 1.1, 1.2, 1.3, etc., and we get to 2. Okay, when we get to 2, this link reaches full capacity. So that freezes the flow rates of flows 3 and 4. Now they can't be grown anymore. And then you continue to grow flow 2. 2.1, 2.2, up until it's 6. And when it gets to 6, this link over here reaches full capacity. Okay, and so that's how you do the algorithm. No matter how complicated the network, you just sort of take all the flows, and it's as if you're pouring water into or you're increasing the rates at which they pump water through a network. And you just make sure you increase them all at the same rate. And once the link reaches full capacity, you stop turning the knobs for those flows that any flows that go through that link. But you keep turning all the others that have not yet are not yet going through a link that's reached full capacity. You grow them all at the same rate. You turn the knobs at the same rate. Okay, and that's it. Just when it reaches full capacity, you stop turning the knob, and that will give you the max pair allocation. Yeah, Faisal.
Oh, no, I didn't see it. Okay, never mind.
Okay. Yeah, Ron.
What are the subscripts? What labels, I should say, on the flow going into number 8?
Oh, these are the rates that we were playing around with. So this is 2 plus epsilon, 2 minus epsilon, 1 and 1. You got here late, Ron, so you probably missed the most important part of this topic, which is that it's not going to be on the final.
Just like the first one.
Okay. A true academic. No? All right. So any other questions? Okay. Okay, let me just jot down the list of topics that you'll be responsible for. Okay, so first of all, there's the pre-midterm topics, which won't be the focus of the exam, but some of the stuff we learn there may still crop up, right? So right, that E of the sum of xi equals the sum of E of xi. You know how to solve these. Exponential distributions, memory property. Right, all this is fair game. It won't be the focus of the exam, but if it, if it can come up in a question, it may. Little's law. But of course, we saw how that could be used in a network setting. We talk about reliability. Okay. We've got the network layer. And routing algorithm. All right, there's shortest path, minimum spanning tree. Right, for this there was which was centralized, and the Bellman-Ford, which was distributed. Okay, some tries, however they're pronounced. That's what Professor Misch covered. Oh. And with the Bellman-Ford, you should know like poison reverse. The question? Doing topics, round robin, LiPo, weighted fair queuing, rough models and finite state machines of these. And there's a transport. Reliable transfer protocols. Go back N. Selective repeat. One bit alternating. Right, using FSMs. Congestion control. Fluid models. Why AIM works. Additive increase, multiplicative decrease. Fluid models that show congestion collapse. And leak bucket. Mechanism. That's really it. That's all the material. Yeah, Ezra.
You're going to ask questions on the data link layer? You're going to ask questions on the data link layer?
The data link layer. No. There won't be any question that's focused on the data link layer in particular. So the memory list property is still game if it somehow crops up in the transport layer. I don't think I would ask anything about the minimum spanning tree and application to lands. Okay, that won't be on the exam. Which is essentially always in the data link layer after the midterm. Yep.
Bye.
Proof by induction. Yeah, that could show up, but they'll be simple proofs. I mean, anything I put on the final, the right answer can be done with like a 4-line proof. I'm not gonna ask for anything that's gonna require pages and pages and pages. If you don't do it the right way, I mean, I can't promise you your answer won't look like that. But the point is, there will be a right answer that is very simple. All right. So proof by induction, proof by contradiction. Yeah, those might be on there. I mean, those are methods that we used when we talked about the routing method. And it is useful. I mean, a grad student of mine and I, some work we're doing now, we actually just proved a new result using proof by contradiction. So, and again, the proof is simple but non-obvious. It took us a while to realize that you could get it in such a compact form. So it's a good thing to know, in my opinion. Okay? If nobody else has specific questions, we can just wait until review on Friday and let you out of here early today. That is, if no one else has any questions. Yeah, question? Or? No? Yeah. So expect about four questions on the final. That'll be my guess. Yeah, Ron. It's going to take, we're going to have 3 hours. I have never given an exam where people have left early. I'm very bad at, yeah, that's true. That's true. I always take the exam. I think, all right, I'll make it a little easier. I'll make it a little easier, and yet, I mean, my exams tend to make you think. So, I don't know. It can be done quickly, but never has. So, all right. See you Friday.